So we are looking at Unit 8 on acids and bases. This is Topic 1, Intro to Acids and Bases. So we will be looking at calculating the values of pH and pOH based on Kw, or the equilibrium constant of water, and the concentration of all species present in a neutral solution of water. So we're going to take a look at Bronsted-Lowry acids and bases. So this is one definition of what an acid and a base are. There are multiple out here, but this is what is used in AP chemistry. So at the basic level, or at the most simple level, Bronsted-Lowry said that acids are chemicals that donate a proton, and that's hydrogen or hydronium ion. We'll discuss that, what that means in a second, in solution, while bases accept that proton. So why do we use the word proton? Well, what's really being exchanged here is a hydrogen ion, H+, okay? So if we think about hydrogen, it has a positive nucleus with one proton, and then it has one valence electron. That's the structure of a hydrogen atom. But if we erase and take away that proton, that electron, then we just have a proton left. So a hydrogen ion, an H+ ion, is really just a proton. So that's why they say it donates a proton, and that a base accepts that proton. So another way of saying that is that it donates a hydrogen ion or accepts that hydrogen ion. We can also see H3O+. So we're going to see where that comes from as we go, but basically if a proton or a hydrogen ion is produced by an acid, it can join with water in solution and become H3O+. So if we added a hydrogen to water, we get hydronium ion. So this exchange of hydrogen ions is what drives acid-base reactions. That exchange is what we're going to be looking at throughout this unit. So let's review conjugate acid-base pairs from Unit 4.8. So this is looking back at Unit 4, what we finished at the end of last semester, and how we can see how acids and bases behave in a reaction and identify the acid and the base and their conjugates, okay? So if we have an acid, it's going to be our reactant. So again, the definition of an acid is the one that donates or gives away a hydrogen. If we look at this reaction, we've got HCN, and that becomes Cn-, so it got rid of its hydrogen. So that is our acid. So the acid is always going to be on the reactant side, so is our base. Now the conjugate is what is formed when it gets rid of that hydrogen, what's left over. So the Cn- is what's left over when we get rid of that hydrogen. An acid and its conjugate base creates a conjugate acid-base pair, and they are different only by a single hydrogen ion. Now you notice that the charge also changes. We go from having no charge, HCN, it's neutral, but if we give away a hydrogen ion, H+, we give away a positive, our ion has got to be negative, so we get Cn-. Charges do matter. You've got to make sure you're writing those charges in, okay? So what about the base? Well, the base is the thing that is taking the hydrogen. So if we look at our reaction, the other reactant is liquid water, and so that has to be our base. And what it becomes is H3O+, also called that hydronium ion. So it took that hydrogen that HCN had and gained it and became H3O+. So the acid gave the base its hydrogen ion. So the water and the hydronium ion are a conjugate acid-base pair, again, different by only one hydrogen. Notice that when it gained that hydrogen, it gained the charge that came with that hydrogen. It went from being neutral, gained something positive, so it becomes more positive. So let's take a look at another example. So let's take a look at another example here. We've got, we're identifying the sets of conjugate acid-base pairs in the reaction. So just like our last one. So I like to look at my reaction and see where is that hydrogen going, right? Where is it starting? Where is it going? We can see on the left side, both chemicals have hydrogens in them. We can see on the right side, we get CH3, NH3, that has an extra hydrogen. And then we have OH-, so that lost a hydrogen. So the chemical that lost the hydrogen must be the water. So that must be our acid, right? Acids donate hydrogen ion or a proton. And so it becomes OH minus. That has to be our conjugate base. So those two, again, are different by one single hydrogen. And as we give away that H plus, it becomes the other ion is negative, so we get OH minus. So that means the other chemical or the other reactant has to be our base, CH3NH2, and that chemical is adding the hydrogen, gaining the hydrogen. So that's why that chemical is the base, and it becomes the conjugate acid. So it gains that hydrogen ion, gains that positive charge, so we get CH3NH3 plus. So again, these are conjugate acid-base pairs. We get two pairs in each reaction, and each pair is different by one hydrogen ion. So we've got water giving its hydrogen to the CH3NH2 and becoming that hydroxide. This one, the CH3NH2 gaining that hydrogen and becoming its conjugate acid product. So it's just an exchange of hydrogen ions. Acid-base reactions are sometimes looked at being very complex when they are a simple exchange of one atom or one ion between the two chemicals. So that's what we want to look for. We want to track that hydrogen. You're tracking down that hydrogen. All right, that's your battle. So in both of the previous questions, we got to see water react, but it acted as both an acid, where it donated a proton, and as a base, where it accepted a proton. So we're going to see how this process occurs in just pure water without another chemical involved. So this is called the autoionization of water. Okay, so if we have a water molecule like we do here, it can give away a hydrogen, okay, to another water molecule. When it does that, it gets rid of that hydrogen, it becomes OH, and then it has that negative charge, right? Got rid of a positive, so it's going to become negative. The other water molecule gains that hydrogen. Now it has three of them. That's our hydronium ion, and it gains that positive charge that came with it. So that reaction is called the autoionization of water. Well, why is it auto? Well, this automatically happens in any container of water. So if we get that deionized water from our class that we use for labs, a very small percent of our water molecules will do this automatically. Okay, we can't stop it. It's just happening. So if we look at our reaction, our acid and our base are both going to be water. So our acid's water. Well, when an acid reacts, it gives away a hydrogen. So that means its conjugate has to be the OH minus. Okay. Now our base again is water because that's our other reactant. And its conjugate acid, when you gain a hydrogen from the other water molecule, is that hydronium ion. Okay, so this is the autoionization of water. There's a small, again, percentage of water molecules that will do this automatically. But this helps us in figuring out pH and figuring out some other values for our acids and bases. Now, this chemical reaction for the autoionization of water is shown. We've got it written below where we've got those two water molecules. Oops, there we go. Two water molecules as liquid, we get the hydronium and the hydroxide. Now, the other value, along with the reaction, we are given a value called the Kw. Now, capital K, we are used to seeing in this unit and the last one, is our equilibrium constant. The little w signifies that this is the constant for water. So this is that equilibrium constant for the autoionization of water. We could write a equilibrium expression for this reaction, again, products over reactants. So we have the hydronium and the hydroxide, but our reactants are liquid, pure liquid, so we don't get a denominator on this one. So if we multiply that hydronium and that hydroxide ion concentration, we're going to get our Kw value, which happens to be 1 times 10 to the negative 14th. Okay, this thing there is, though, this is only true at 25 degrees Celsius. We've talked about how an equilibrium constant is dependent on temperature. If we change the temperature, we change the constant. So this one is very specific. It's going to be that value at 25 degrees Celsius. Now you can calculate Kw, or you might be given a Kw at a different temperature, but most of the time we're going to see it at this temperature. Now there is an alternate form of the equation. Sometimes instead of writing two water molecules and showing that exchange in the hydronium and the hydroxide, we kind of simplify it and we say, hey, water breaks down. Some of them, we got the hydrogen, it separates from the hydroxide. This is our auto ionization water, right? So we've got our hydrogen ion that gets donated or given up, and then what's left is the hydroxide. So this is another way of writing our Kw expression. Hydrogen times hydroxide concentration gives us that same Kw value. This one, I believe, is the one that's on your AP equation sheet, so that might be the one you become more familiar with. But remember, H plus and H3O plus, those are interchangeable. They mean the same thing, okay? So we can write them either way. It's not a big deal which one we use. So let's talk for a minute about pH and P. So what is the P for in pH? So the letter P in symbols, and we're not just going to use pH, we're going to use pH, POH, pKw. We've got this P in front of things, right? So what does the P tell us? It's basically telling you to take the negative log of a quantity. So you've got a number, you've got a concentration of something, and you're going to type into your calculator negative log and put that number in. That's all the P is telling you to do. It's giving you instructions, okay? So it's not something we have to always jump to our equation sheet for. You see that P, you're going to say, oh, that's negative log. I just got to type in negative log, type in my concentration. So the concentrations for ions, such as hydrogen or hydroxide, in aqueous solution have units of moles per liter or molarity, right? pH or POH, and we're going to talk more about what POH is, but it's calculated from a logarithmic function, right? And the pH or POH does not have any units, so logarithmic functions are not going to have units. When we take that log, it's like the units disappear, okay? So remember, again, that H3O plus and the H plus concentrations can be used interchangeably, so if we see one, that means the other one, same thing. So what does this all mean? So if we know the value of our concentration of hydrogen or hydronium, we know how much H plus there is, you can calculate the pH of a solution, okay? So again, that P means take the negative log. So our pH is negative log of hydronium or negative log of hydrogen. The one on the right is the one I'm more familiar with and I'm more used to because the H and the H kind of match each other. Now, if we had the pH of the solution, we can also calculate the value of the H plus, right? We could reverse the process. So to undo a log, we have to use the opposite operation. Well, that's convenient because on our calculator, if you hit the second key and then the log button, it has its inverse, which happens to be on your calculator 10 to the x. So if I have the pH, say my pH is 4.2, I do 10, that inverse log, so 10 to the negative 4.2, and I get my hydrogen ion concentration. So we can get a concentration of a specific ion from pH. We can do the same thing with POH, okay? So if we know the value of a concentration of hydroxide, again, that base concentration basically, you can calculate the POH of the solution. So POH equals the negative log, so that should be OH. Let's fix that. Sorry, I'm writing with my finger here. It's not pretty, but POH is the negative log of the hydroxide, the OH. So we, again, hit that negative and the log button, we put in the concentration of our hydroxide, we get POH. And we'll talk about how pH and POH are similar but opposite scales from each other and what they really represent on the next slide. So if you know the POH, man, I messed that up twice. I must have copied and pasted. So if we know the POH of the solution, we can calculate the value of hydroxide as follows. Same idea. It's the inverse of that negative log. So 10 to the negative POH gives us our hydroxide ion concentration. So we've got ways to kind of go between having a concentration and finding a pH or a POH. They like to find those because those are things we can measure in a lab very easily. But if we can measure a pH or a POH, we can also reverse it, right, back to our concentration of those ions. So these are really important equations. Now, the ones that are given on the AP exam would be finding your pH and finding your pOH, okay? They don't have the inverse of that. It is assumed that you know how to do that from your math classes. But again, it's just that inverse, that second and then the same button. Instead of hitting negative log, we're gonna hit second log and then put in negative pH or negative pOH. So it's not too bad, and we're gonna do some practice with that in terms of the equation. Now, before we get more into these, I wanna talk about significant digits or significant figures in pH, pOH, these type of numbers, okay? So you'll see in your original number over here, this one has a single significant digit, just one sig fig. With pH or pOH, only the digits to the right of the decimal point are considered to be significant. That number in front is just kind of giving you where on the scale it is. The numbers to the right are telling you how precise it is. Okay, so if it's got one sig fig, we're gonna have one decimal place. This second one has two sig figs, we're gonna have two decimal places, so 2.92. If we got 3 sig figs over here in the concentration, we're gonna have 3 decimal places. Okay, and I'm gonna remind you of this as we go through calculations so you can get used to it, and that's just when we find pH or pOH, okay? So your decimal places are your significant digits. All right, so we're going to talk about the pH and pOH scales and what's going on with those. So what do they really represent? So again, pH, it goes from 0 to 14 and measures the concentration of hydrogen ion in solution. It is possible to go outside of the 0 to 14 scale, but at this level, that's what we're going to see. So if we look, we've got pH listed up at the top here, and we can go 0 to 14. You notice this rainbow. This really represents a lot of our acid-base indicators, especially what's called universal indicator, where if we use that, that indicator, we're going to get these kinds of colors at these pHs for different acids and bases. So a low pH here corresponds to a high amount of hydrogen ion. So our concentration of hydrogen ion is given here, and that's 10 to the 0 to anything to the 0 power is 1. So this would be a concentration or a molarity of 1. Okay, molarity of 1 would give us a pH of 0 of our acid. Now, if I had an acid and its molarity was, we'd move that decimal, so it's 0.1 molar, right? We drop that molarity down by factor of 10, now we have a pH of 1. We increase the pH as our concentration decreases. So we can see if I went down, here, I'd have 0.0001. I think that's right, 0.0001 molar acid or hydrogen ion. And that would correspond to a pH of 4. That's less acidic than our pH of 0. And as we get towards the middle here, our middle is a pH of 7. We consider a pH of 7 a neutral pH. So that's a pretty small amount of hydrogen ion. Now we can keep going and we can get to our smallest concentration of hydrogen ion, which is 10 to the negative 14th. So imagine a decimal with 13 zeros and then your 1, right? That's a pretty small number of hydrogen ion, pretty small molarity for our hydrogen ion. So that corresponds to a high pH. So when we look at the pH scale, the exponents correspond to that pH. You'll see there's a match there. The smaller the negative power value is, the lower the pH, the more closer it is to that top of the scale, and the more acidic the solution is. So these colors we see with the yellows and the oranges, getting into that light green, that kind of thing, those are all of our acidic side of our pH scale. Those are our acids, our stronger and sometimes weaker acids. Strong acids are going to be way down here at the 0-1 range. Now, pOH is very similar, but instead of talking about the concentration of hydrogen ion, we're going to talk about the concentration of hydroxide ion, which typically is associated with bases. Lots of our bases have hydroxide. For instance, one of our common bases is sodium hydroxide. We used it in our titration lab, the NaOH. So, and it works similarly. If we have a pretty high concentration, so this would be our 1 molar concentration of hydroxide ion, we would have a pOH of 0. But you notice we'd have a pH of 14. So these are opposites of each other. As we decrease that concentration of hydroxide, we're going to increase our pOH. Right, so we're going to get our most basic solutions on that blue-purple end, our most acidic solutions on that red-orange end, and neutral in the middle. And you'll notice as we look across the scale from one side to the other, what do all these numbers add up to? They add up to 14, no matter which line we're on. Okay, so pH plus pOH equals 14, and that is an equation that we're given on your equation sheet, which is pretty convenient. So that's our fourth little bullet point over here. So these are our scales, and again, they're a logarithmic scale. Every time we go up by 1 pH value, we're making our concentration 10 times smaller. That's why it's a log scale. So every time we increase this number by 1, we decrease our concentration by 10 times. Okay, that's how logarithmic scales work. And we use that to kind of make our numbers easier, right? We don't have to look at these giant, crazy numbers. We can just look at this pH scale and get a relative idea of what's going on.
All right, so pH is the measure of the concentration of hydrogen ion, hydronium, in solution, as a reminder, and pOH is that measure of the concentration of hydroxide ion in solution. And those two scales are opposite of one another. So if we're at 25 degrees Celsius, a basic solution would have a hydronium ion concentration that is less than the hydroxide. Okay, so if hydronium is less than hydroxide, then it's more basic. Remember, when they're equal, they're neutral. So if we have basically more hydroxide, we're going to have a more basic solution. But Kw will still be equal to 1 times 10 to the negative 14th because it's still at 25 degrees Celsius. Alternatively, in an acidic solution, we have more acid, so we're going to have hydronium will be greater than hydroxide. But again, Kw at 25 degrees Celsius is still equal to 1 times 10 to the negative 14th. So if we know one of the concentrations, either hydrogen or hydroxide, and the solution is at 25 degrees Celsius, we can find our concentration of the other ion.
Okay, so let's take a look at calculating those pH and pOH values and undoing them with the calculator as an example here, and run through an example real quick, and then we'll do some more. So basic example, we know that pH equation is the negative log of the hydrogen. So if we had a hydrogen ion concentration, so we've got an acid or a base, and we know that the concentration of H plus is 1.2 times 10 to the negative 3. Again, if we want to find the pH, that P is going to scream at you, take the negative log. So we want to take the negative log of that concentration, 1.2 times 10 to the negative 3. So if I was to put that in my calculator, I'm going to hit the negative button. We've got that down here at the bottom. And then I'm going to hit that log button, right? And I'm going to do my scientific. It's going to automatically put a parenthesis. I'm going to put my 1.2, my times 10 to the negative 3, and close my parenthesis, which actually you don't even have to do on these, just so you know, and hit enter, and we should get 2.92. I do want you guys to grab your calculator out, especially if you've got one of the graphing calculators or you have one a little bit different. Make sure you know where the location of these numbers. We've used logs before, more the natural log actually, which is underneath, but we want to make sure we know that we're typing this in correctly, right? So pause the video, type it in, make sure you got it. You're getting 2.92. Okay, so hopefully you have practiced that. Now let's review significant figures. Again, we got 2 sig figs in our answer, or in our concentration, which means we're going to get 2 decimal places on our pH. pH values, only what's after the decimal is going to be significant. That number up front just kind of moves things around, gives you a scale. So what if we wanted to reverse this? We wanted to undo our pH, and I'm given a pH, I measure it with a pH meter in a lab, and I need to know my hydrogen ion concentration. Well, we can reverse that. So when we want the hydrogen ion concentration, we're going to use the same button. We're still using that log button, but we're going to use the inverse, which is when we hit second. So to do 10, or to find the hydrogen ion concentration, we're going to do 10 to the negative pH. So we're going to hit second, we're going to hit that log button, that's going to give it 10 to the, and then we're going to hit negative and our pH value. So in this case, we could do second, log, and then negative 2.92. And we should get 1.2 times 10 to the negative 3. Again, if our pH has 2 decimal places, then we're going to keep the first 2 digits on our concentration. And we would throw the molarity at the end of that because we are looking for a concentration. So that part does have units. pH and POH do not have units. So again, these 2 decimal places give us our 2 sig figs here. So that's how we can find a pH and reverse a pH. We can do the exact same thing with POH. The equations don't change. It's just what we're plugging into them. So again, we get that same equation. It's just if I want OH, I got to plug in an OH. So say our OH concentration is 6.8 times 10 to the negative 12. We've got 2 sig figs there. We got that 10 to the negative 12. So that's a big hint that our POH is going to be around 12. We can always estimate that. The 6.8 is going to adjust it down a little bit. So if we plug that in, we do POH equals negative log. So we'd hit that log button. So negative down here, right? And then that log button and type in our scientific notation. That should give us 11.17. Another good one to try in your calculator. Make sure you're typing it in right. Again, 2 sig figs here, so 2 decimal places. And you notice it's pretty near 12, right? I said it'd be 12, but a little lower because of that 6.8. All right, so again, we want to undo it. I've got my, lab set up, and I need to find that hydroxide ion concentration. I got my POH. So we're going to do the exact same thing. We're going to hit that second button and that log button, and then type in our negative. In this case, if we wanted to undo this one, 11.17, so 10 to the negative 11.17, and we get that hydroxide ion concentration. 2 decimal places there. And our pH or POH gives us 2 sig figs. So this process, they're the exact same equations. They're the exact same process. They're the exact same buttons on your calculator. We just got to think about what are we actually putting in, right? We got to look at the numbers and what they're representing. This is another area where it is so important to label your stuff during your equations, right? So if I'm doing all kinds of calculations and at some point I'm calculating a hydrogen ion concentration in H+, then that means I can take the pH and find the pH of that value. But if I'm calculating things and I've got an OH, then if I do negative log, that's going to be a POH. So you just have to pay attention to what you're doing and add some labels in. Make sure you know which value you're calculating. All right, so let's do some practice with pH, calculating some concentrations and pH values, POH values, all of that. So we're just finding the missing information in the table. Let's start in this first, or this column here, and we're going to start with the last 2 boxes. We're just going to practice finding pH first. So we've got some hydronium, again, another way of saying H+. We got those H+ ion concentrations. In molarity, we can see this is a high molarity, this is a much lower molarity, so we should get a lower pH here and a higher pH here. We want to think of those, again, kind of opposite of each other. So again, for those, we take the negative log, again, P, that P in front should scream at you negative log of your concentration. And if we do that, again, try it in your calculator, we should get 4.37. Why don't you guys pause for a second, try the next one, see if you can agree with me on your calculation. All right, so you should have calculated the next one. Again, we want to find pH, so it screams negative log at you. 0.015, and we get 1.82. Okay, again, both of these given values on the left side have two significant figures, so we get 2 decimal places in our answer. And like I said, this has a higher concentration, so a lower pH. This would be more acidic than this one. Now, if we want to reverse the process, we're going to do 10 to the negative pH to find those. So I do 10 to the negative 11.65, and I should get 2.2 times 10 to the negative 12. Again, this has 2 decimal places in our pH, so 2 sig figs in our concentration, and I should be putting molarity after those. There we go. I'm going to go ahead and throw an M over here for the next answer. So once you try the next one, make sure you can get to an answer. Try it in your calculator. Pause for a second. All right, we should have done 10 to the negative 6.14, and we get 7.2 times 10 to the negative 7 molar concentration. So that's how we can find our hydrogen ion or hydronium ion concentration. Again, those are interchangeable. Now, if you notice down the bottom, it has a little statement. So as our value for the concentration of hydronium or H plus ion increases, so as we go get bigger and bigger values going this way, the value of our pH is decreasing, right? We're getting smaller and smaller pHs because we have more and more hydroxide, right? We talked about how the more, not hydroxide, goodness, more and more hydrogen. The more hydrogen you have, the lower your pH, the more acidic it is. Okay, let's go over to the hydroxide side. That sounded weird. So we've got, again, we're gonna start at the top here. So we've got a POH. We want to undo that. We want to find a hydroxide ion. We should do 10 to the negative value, so 10 to the negative 10.39. We got 2 decimal places there, so 2 sig figs. 4.1 times 10 to the negative 11th. Notice again that our exponent is very near our value here. So we can estimate this is 8.04. We're probably going to have an exponent around negative 8. All right, why don't you try it? See if you're getting something around negative 8. All right, we should got, ooh, close, right? So 10 to the negative 8.04, we get 9.1 times 10 to the negative 9. So it's not always going to match 1 to 1, right? Just because this is 11 doesn't mean this is 11. Just because it's 9 doesn't mean the POH is 9, but they're close to each other, right? They're going to be in the same neighborhood. Okay, so if we have pH or POH, we're going to do 10 to the negative to undo it. All right, down here, we're finding POH, so we're finding it. It should scream 10, it should scream negative log at you. All right, so negative log of 6.8 times 10 to the negative 6 molar, we should get 5.14. Again, that number, 5.17, close to 6, right? Our exponent. All right, try the next one, see if you get the same answer. So we should get 3.55. Again, negative log 2.8 times 10 to the negative 4, 3.55. So it says as the value of hydroxide increases, so as our value increases, again going down because we're getting smaller, our negative exponent is getting smaller, so we're getting larger values here. Our P, and it says the value of pH. Well, right now we only have the value of POH, so we're going to calculate that last column before we finish answering this. Got a little ahead of myself. So pH and POH, we mentioned this quickly before when we were looking at that picture of the pH and POH scale. But remember how the two sides always added up to 14, right? pH plus POH equals 14. So if we have either of those, we can subtract them from 14 and find the other one. So I can do 14 minus 10.39. We want to keep those same 2 decimal places so we have the right number of sig figs. So however many decimal places are in your measured value, we're going to keep, and we get 3.61. Okay, so that's our pH. So we can do that for all of these. 14 minus the POH is going to give us our pH. So we should get 5.96 on the next one. 8.83 on the following, and 10.45 on the last one. So we can see as our POH concentration goes up, our pH increases, right? We get bigger and bigger pH values. So hydrogen, hydroxide, those are opposites of each other, right? And so those scales are opposite of each other. All right, so we're going to do some practice with pH. It would be a good idea, I'll do a line of them with you, and then it'd be a good idea to pause and work through your calculations, really practice, so that you can see if you've got it down, and then check your answers, okay? So we've got, in our first column, the hydrogen ion concentration, then second column, we're looking for pH, OH minus concentration, POH, and then is it acidic or basic? So I've got a hydrogen ion concentration. The first thing I want to look for is my pH. That P is going to scream at you. That's right, negative log. So we're going to do negative log of 0.075 and we get 1.12. All right, this is also a good opportunity to follow along with your calculator and check your work. Now, we have some options. We haven't looked too much at the KW equation yet. We will get there. We'll use that more later. But actually, I want to show you guys one real quick. So KW, right, we talked about earlier, is equal to the concentration of hydrogen times hydroxide. And this value for KW is 1 times 10 to the negative 14 equals our hydrogen times hydroxide. So if I have hydrogen or I have hydroxide ion concentration, if I have either of those, we can divide by whichever one we have and get the other one's concentration. So for instance, I'm looking for OH, right? I want to find that. So if I divide this by my hydrogen ion concentration, 0.075 molar, then I should get my hydroxide ion concentration. So if you try that out in your calculator, what you should get is 1.32 times 10 to the negative 13. And actually that would be 1.3 times 10 to the negative 13. My sig fig was off. Got a little confused there. Okay. So if we do that, that's one way to find your hydrogen or hydroxide concentration from the other one's concentration, how those two relate. That's a nice thing. All these equations kind of relate to each other, so they kind of create this chain and you can go in any direction. Now our POH, that P screams negative log at you, so negative log of 1.3 times 10 to the negative 13th, we get 12.88. Now if we want to figure out if it's acidic or basic, acidic is going to be when our hydrogen ion concentration, sorry, it's not looking great with my finger drawing it, is greater than our hydroxide ion concentration, or when our pH is lower than 7. So this one should be an acidic solution. All right. Now, using those equations that we've talked about, why don't you try one more? Try the next one. Okay, or try all of them, and then we'll check them, okay? So, hopefully you've tried the next one. We got 5.63 as a pH, so we need to undo that pH. We're going to do 10 to the negative pH, so that will give us our H+. So 10 to the negative 5.63, gives us 2.3 times 10 to the negative 6 for our molarity of that hydrogen ion concentration. I've probably left my molarities off this whole table. Please forgive me. Okay, now we have options. So say we wanted to go to POH, right? We could do 14 minus 5.63 and get that value. Or if we wanted to go to hydroxide, we could use that KW equation up here. Either way, our next concentration, so it looks like going between H plus and OH minus. In this case, we get 4.3 times 10 to the negative 9th, and our POH is 8.37. So you could do 14 minus 5.63, that gives you the 8.37. And then you could do 10 to the negative 8.37, get 4.3 times 10 to the negative 9. Whew, that's a lot of numbers. So let's compare. We've got a low pH, we've got a high pOH. That is going to tell us again that it is acidic. Okay. So if we start to kind of reverse engineer this one, we've got a hydroxide ion concentration. So easy thing to get to is your pOH. We want to get that P, so we're going to negative log it. Negative log of 3.8 times 10 to the negative 7th is 6.42. Those 2 decimal places for those 2 sig figs. All right, we could do 14 minus 6.42. Let's go the wrong way. And get our pH 7.58, right? A little above 7. And we could do 10 to the negative 7.58, 2.6 times 10 to the negative 8. Right, so we're just manipulating these same equations, same equations, right? To find the hydrogen ion, we're going to do 10 to the negative pH. Ooh, this is hard to draw. Negative pH. To find our pH, we're going to do negative log, right? That's going to scream negative log at us of our H plus. And then same thing over here, 10 to the negative pOH or negative log of P of the OH. Okay, finally we've got our pOH. We can undo it. 10 to the negative 4.54 gives a, oh, I forgot to say that this one was basic. Sorry. So pH higher than 7, pOH lower than 7, that's basic. Okay, so we got our pOH, 4.54. So we undo it. 10 to the negative 4.54 gives us 2.9 times 10 to the negative 5. Again, molarity. All of these are molarity because they are a concentration. And then if we want to do pH, we could do 14 minus 4.54, 9.46. And then undo that pH to find our hydrogen ion concentration. So 10 to the negative 9.46, 3.5 times 10 to the negative 10 molar. All right, that's a pretty low hydrogen ion concentration, very tiny. Much higher hydroxide, so that's got more the hydroxide, that's more of that base, so it's a basic solution. Okay, so lots of ways to go between these equations, as you can see. So to wrap us up, we have looked at what an acid-base reaction is. It's an exchange of hydrogen ion. And when we do that, we can identify the acid and the base and the conjugate acid and base, and find the conjugate acid-base pairs. So if you're looking for those pairs, remember they are only different by 1 hydrogen. It should be essentially the same chemical, we just move the hydrogen, right? Gave it up or gained it. And with acid-base chemicals, we get into pH, right? So if we see a P in front of any of these pH, pOH, we're going to see pKa later, pKb, these kind of things. When you see the P, you take the negative log of whatever thing comes after it. So pH, we're going to take the negative log of the H concentration, right? And that we can, all these equations really relate to each other. pH and pOH add to 14. We've got hydrogen times hydroxide gives us our Kw. So there is a relationship between all of these values, and we can use those things. So going forward, as we get into the equilibrium part of this unit, we're going to be using pH and pOH to help us find those concentrations and be able to, complete rice tables, things like that, later on. So that wraps us up, and we're going to move on to topic 2. Thanks, guys.